Hello, this is Brett Estrade, picking up with my talk from the other day at the Perl and Reiku conference in the cloud. I went over, so I wasn't able to go into any demonstration of the module that I was using for some of these examples, and as a result of the investigation I'm doing. However, I wanted to start here, and I have no time limit set, and so this may go on for a while or may wrap up quickly. But in any case, my aim is to inform and not waste your time. But we do need to talk about the example from the original talk. I had introduced this concept of this execution, this parallel execution that could operate over two CPUs. One line of execution on CPU 1 here consists of task A, B, and C, and then the second parallel and independent line of execution consisted of task X, Y, and Z. Within each thread or within each line of execution that is on the each CPU, there is a total ordering. So A has to happen before B, B has to happen before C, and then similarly on CPU 2, task X has to happen before task Y, and task Y needs to happen before task Z. So within each line of execution, the tasks are totally ordered, and then between the two lines of execution, they are partially ordered, which allows us to interleave tasks that are not directly dependent on one another. And what you have at the bottom, so this top dependency graph is the parallel execution. The question we're addressing is, what does this look like if we wanted to run these tasks in a properly ordered way on a single CPU? So we're reducing the parallelism from two CPUs to one CPU. And the bottom dependency graph is an example of what you may get, and it is consistent with the total ordering that is implied on each CPU in the parallel execution. And it's also valid when you consider the potential for partial ordering between the two lines of execution. In this case, it's just a simple A, B, and C happen before X, Y, and Z. And the execution order I have described as a string here at the bottom in the white box, A, B, C, X, Y, Z. And then I also covered this slide in the original talk. This shows all of the valid orderings of the execution that maintain the total ordering among A, B, and C and X, Y, and Z, but then allow for the partial ordering to be effected as an interleaving of the tasks between each of the executions, that parallel executions. And in fact, there's 20 of them. There is a way, by the way, to compute, combinatorially count how many different orderings one may get, but that's not the scope of this talk. But I'm sure somebody may have been wondering, how do I know there's 20? Well, in this case, I literally just listed out all of the possible paths using one of the tools that I'll talk about in a bit. All right, so this is another slide that just shows the valid orderings and that they are all valid within the context of the parallelism that is being described in this flow or this dependency diagram of the parallel execution. So how can we serialize arbitrary dependencies? The question is, how do we turn parallel execution or dependency graphs that admit parallel execution into a singular line of execution? The trick is to respect the total ordering that is inherent in each line of execution, but also allow for us to express the different combinations that the freedom that the partial ordering among the lines of execution give us. And what we talked about in the original talk is that this looks like a finite automata. And finite automata, in fact, has some ability through some of the algorithms that are used to convert from regular expressions to automata to handle this the constraint of total ordering, and also admit the possibility of interleaving the partially ordered tasks or states. I talked about finite automata. I'm going to skip over these. Finite automata are the graphical representation of regular languages. Regular expressions necessarily define and equivalently define finite automata. And in this talk, we talked about deterministic finite automata and its regular operators, concatenation, union, and the clean star, or it's also known as closure. Then there's non-deterministic finite automata. It has the same three common operators when we're talking about the regular expressions describing the automata. And then there's parallel finite automata. Now this includes the three operators that we're all used to, plus the shuffle operator. The shuffle operator is sometimes called an interleaving operator. But one interesting note is that a parallel finite automata that expresses some combination of languages using the shuffle operator is equivalent to a binary Petri net. And this is shown in that 1994 Stotts and Pugh paper, which, if you're interested in this topic, even if you're just interested in formal languages and finite automata, I strongly recommend you read that paper. It is really neat. All right, so shuffle operator, I think I talked about this, but it's the and to union to or. And that it makes sense that there would be maybe this missing operator that most people don't use or implement. I believe that's because maybe it's not obvious why this is useful. Well, this is a case. What we're talking about here is a case of how to describe parallel semantics among, say, valid strings or characters, and then have some sort of algorithmic way to reduce the parallelism is a good use case. And maybe it's non-intuitive, because why would you want to go from more parallel to less parallel? Well, there's some interesting reasons. I think that this is one of them that we're talking about here. Now, the shuffle operator, this is just an example of how it works over two regular languages. In this example, you've got language 1, which is just the string AV, and you've got language 2, which is just the string CD. Now, if I want to shuffle L1 and L2, I'm saying that I want to bring them together in such a way that valid strings resulting in the language from the shuffle, it's a combination of all valid strings from L1 and all valid strings in L2, but all combinations of them as it may appear as if the valid strings from each language are interleaved. Now, this is a good example. That's a mouthful what I just said, but what this says, well, the valid strings I have enumerated here, there's 5 of them, and then it's simply AB and then CD, AC, BD, AC, DB, CA, DB, CD, AB. And you'll note it maintains the total ordering within language 1 and then the total ordering within language 2 of the single strings that consist of the language, which is AB and CD. But it also presents the final valid strings of this resulting language as the combination of all valid strings from both of the languages in all interleaving orders. So it expresses the partial ordering that is inherent among the valid strings within each constituent language, but also enforces the total ordering of the valid strings that are in each individual language. Okay, so in that flat module, I've implemented 15 years ago, the ability to convert regular expressions into DFAs. And the way that I did that was simply by implementing the published algorithms that have been well known for some time. Going from RE to NF, regular expression to NFA, you would parse the regular expression and create an abstract syntax tree, and then you would you would perform what's called Thompson's construction, which is a traversal over this abstract syntax tree. And when different operators are encountered, the finite automata, or the directed graph, is built up using certain elements based on the tree itself. So it's literally just traversing the tree and building up this directed graph based on the traversal and the subtrees that are present when an operator is hit. Now, NFA, going from a non-deterministic finite automata to deterministic finite automata, you would use something called subset construction, and that basically it discovers all of the same states that through some like creation of, I describe it as a creation of buckets, and then it determines which of these buckets are equivalent, collapses those buckets down into single states, and that's how you get out of this non-deterministic finite automata all of the actual deterministic states that are present. And then once you have a DFA, deterministic finite automata, we necessarily have to enumerate all of the valid strings. Well, we started with a regular expression, and the best way to do this is simply to implement a depth first traversal of the DFA, taking it as a directed graph from the start state to an accepting state. And if you accumulate the labels along the way, which are the valid symbols, then you will necessarily be constructing all the valid strings that are described by the language of the DFA. And this is also a good example, or good place to point out why I haven't currently done anything with creating these pre-plans or these parallel regular expressions with the clean stars, because it admits cycles, and there's no neat way to just go from a start state to an accept state. You have to make decisions. For example, which cycles do I want to iterate over? Which cycles do I want to traverse? How many times do I want to traverse them? So there's some questions, open questions related to that as far as the usefulness. I believe that it is very useful in this case for what we're doing here with SoGenius, but that remains to be seen, and I'll make no claims at this time on what can be done. So we're dealing with finite languages, and so that means that the number of strings that are accepted by these regular expressions, these parallel regular expressions, and then the automata that they imply is finite. And you can list them out, and there is a beginning of this list and end to this list. This is talking about converting these parallel regular expressions to DFAs. So the PRE is a parallel regular expression. It is a regular expression that has a shuffle operator in it, and the result is a parallel finite automata. The parallel finite automata is created in a much similar way as going from a regular expression to an NFA, a recursive descent parser. It creates an abstract syntax tree, and then there was an algorithm. It was a modified Thompson's construction that was introduced in the Stotts and Pugh paper that introduced a lambda transition in addition to the epsilon transition. So we're basically building in a modified or an augmented non-deterministic finite automata that tracks the shuffling of languages that is indicated with the shuffle operator by adding another element, and that element necessarily includes this lambda transition. And then from there, we go from the PFA to the NFA. This algorithm is published, and it essentially consists of enumerating all of the different interleavings between all of the valid languages for valid strings or valid state transitions for the two languages that are being shuffled. Okay? It's not an efficient algorithm, and there have been attempts to make it more efficient, but it's a very complex thing to do. There's lots of the shuffle necessarily implies lots of additional elements to the language. for additions to the language. And then there's the NFA to DFA using the usual subset construction, and then finally DFA to generate these valid strings. Strings from a finite language, I've talked about this. As long as we don't use a closure or the clean star, there will be no cycles admitted into the DFA or any of the finite automata along the way. So generating these strings is simple. And the reason it's important to generate strings with what we're doing is because the strings represent valid sequential orderings of the executions that are described when we describe it, the relationship, the execution relationship, that we want to using the parallel regular expression. So in our examples, we're just going to be using finite languages, and that's pretty much what it says here. Infinite languages. This is a similar slide to the previous one, but what it says here is if you start using the clean star, you're going to get cycles. And the flat module has a way to basically pump or describe how deeply you would like to iterate into these cycles in these infinite languages. But right now, I haven't looked into how to make this useful or accessible when wanting to schedule the execution or describe some inherent parallelism among some subroutines and executions that could have 0 or more repetitions. I'm sure there's something there, and I'm more than happy to hear from anybody if you have any cool ideas. I just haven't looked at it yet. All right, going back to the shuffle example. So this is looking more. This is the execution dependency graph that we've been working with most of the talk, and now I've converted, or I've drawn it so that it looks more like a finite automata. And in this case, it's a parallel finite automata. You see the initial state is state 0, and you go from there to a lambda transition, which happens pretty much automatically in this case, like in epsilon. And then it splits off into the two different languages, or ABC, and then XYZ, that we are joining through the shuffle. And then there's, at the end, another lambda node or point. And basically what this says is, I didn't think to include a picture here. But if you're familiar with thinking of how a finite automata operates over a string as acceptance is happening, you can look at a lambda transition to mean that there are two different languages that are being shuffled, and there are literally two different languages in their original form are being executed over a given string, and that in order for this combined string or this interleaved string to be accepted, it needs to be accepted by both languages. So that is another, I guess, indication that the shuffle operator implies parallelism, is that inherently you're describing that any valid string that is valid with the shuffled language must simultaneously be accepted by both languages, and that's what this branching off at the lambda and then this coming back together or merging at the lambda on the right hand side indicates. And then of course there's the final state 7. So in terms of execution over a parallel finite automata, that's exactly what our parallel execution was describing. So it matches what, I guess, the semantics of what we want to express here. So the resulting PFA, the one on the top is the original, the graph on the top is the original execution graph. The picture on the bottom is the result of passing in a parallel regular expression into flat or into flat through subgenius, and it's a visualization of the PFA that is created. And then I did this. I'm able to export the graph, the various stages of the graph of the finite automata as GraphViz format or the dot format, and then I just render it using dot or something. in any case, that's how I got this picture. But what we're showing here is this ABC and XYZ. That's a parallel regular expression, and that's indicating that ABC is a language or an execution path, and that XYZ is an execution path, and then the AND symbol indicates that there's independence between those two. So there's total ordering among each language within each set of parentheses there, but then the ampersand indicates that they are independent. But we want to indicate that they're shuffled. So on a high level, this is a way to express parallelism semantically using this shuffle operator. This is the resulting non-deterministic finite automata. It's kind of neat looking, very symmetric and nice. And I dumped it the same way in dot format. This is the DFA that results from subset construction, which I'm sure that there's some symmetry there, or it can be made to look nice and neat, but that's what the dot utility gave me. So not super pretty, but equivalent. And we can see that because this is a minimized DFA from the same thing, and that there we're back to a much better symmetric looking graph, directed graph here. And ultimately, this minimal DFA is what we use to generate all of the list of the valid strings that we showed, all 20 of them. So there's 20 paths from start state 0 to accept state 15, and they all include the proper ordering among A, B, and C, and the proper ordering among X, Y, and Z. However, A, B, and C, that string, is shuffled or interleaved within the string X, Y, Z. And here we go. This is just to illustrate my point. If you take all paths from start state 0 to end state 15, you will necessarily generate all 20 of these strings. And all 20 of these strings are what we're talking about, which is sequentially consistent with the parallelism and execution the execution graph that we showed and have been working with through this talk. This is another one to show. This is a finite. This is the evolution's a bad word, but the stepwise conversion of a parallel regular expression that includes the OR operator from a PFA to the NFA to the minimal DFA. I skipped the DFA because it doesn't really show much that's interesting. But the symmetry of these pictures is interesting, and but I wanted to show an example. So we can define finite dependency graphs as long as we using concatenation, using the OR for the union, and using the shuffle or the AND. But in this case, we're not using the clean star or the closure because otherwise we would have some cycles in there, and then we would necessarily have to deal with those. Okay, so recall the motivation here. I wanted to be able to express some concurrency on a high level and naturally in Perl, and then Perl the language, which I'm contending literally is begging for us to express our programs concurrently. I mean, that's fundamentally that comes from its functional nature and its ability to be highly implicit. That makes us want to describe things in parallel or independently. So that's a natural claim. I feel like it's a natural claim and natural feeling to want to express Perl semantically in parallel, or to describe parallel things. Now, since Perl, the runtime is a uniprocess, that gives us a bit of a problem. There's that, you can call it cognitive dissonance, but it doesn't match the way that we want to think about the language and use the language. Hits a really thick brick wall when we have to consider the environment in which it's running. All right. The whole point of this is that there's a way to be able to think in parallel and also still run as intended in this uniprocess environment. And in fact, we can even use the benefits of both. There's the freedom of expression in the by using the Perl the language to imply parallelism, and then there's the consistency and the predictability of the memory model and the introspection of the memory model that Perl, the uniprocess, the runtime gives us. And I think it results in some interesting approaches to Perl, to writing Perl programs. Okay, so I created this module, and it's called Subgenius. And basically, what it does, it takes an execution plan, which is the string represented as a parallel regular expression, and converts it into one of any number of valid sequential strings. So it takes a PRE and converts it to it serializes it, and then the serialization of that is then used to run the subroutines that may be named the same thing as the words in that PRE in the order described in its serialization. The important part is that the serialization is sequentially consistent. So if we can think about how we want to run a program, we can describe it in a parallel or implicit way. We can then use this module to generate a serialized execution calls of these subroutines, so that it is being done. We can trust that it's being done in a way that is consistent sequentially with how it was described in parallel. Okay. Let's see. Oh, another thing to point out is the serialization can take many forms, as we've seen with that simple call graph that we've been looking at, or dependency graph. You can see there's 20 valid orders. So even a simple parallel regular expression can be executed in many different ways. And then there's the benefit of the fact that these subroutines are being called within a unified Perl process. So that means that we have global memory. We're able to utilize all the cool things that subroutines give us, including being able to pass in parameters and return parameters, and also the give or assign the subroutine's memory from call to call through the state variable or through the state keyword. And I would like to also give credit to my buddy Tio Desian, who came up with the name for this module. I had actually originally called it subsequentializer or something, but it was a mouthful. But he suggested I was asking for better names. This was one of them, and it really stuck because I think it's hilarious and very appropriate. So, but check out his modules. He's got one on Playwright, which is for web browser automation. He's got the Perl module for Playwright. So and he's done some Selenium stuff. He's got neat stuff. In any case, thanks to Tio there. Okay, so this is the execution environment in which we're provided with when we're running something that a serialized schedule that we've been presented with after serializing a parallel regular expression that describes how we want our subroutines to interact. And we've got our global shared memory, and everything's running on one CPU within one Perl process. So we've got the global memory that we're told we can't use or shouldn't use or is not a best practice, but in this case it's a benefit. And then we have a scope, and this is provided for by the Subgenius driver, the run method. And we'll show some demonstrations here shortly. But there's a scope that gets passed from call to call among the subroutines. So it's more or less like an accumulator, or you can treat this as not as something over which these subroutine executions can act as filters. You don't have to use it that way. You can totally ignore the fact that this is happening, but it provides some more or less an execution scope for this. I think Angular, or one of the versions of Angular, has something similar. But in any case, there is an ability to pass something among these subroutines as they are getting called in order. And then finally, we've got the subroutines themselves, and the subroutines you can either just treat them by default and not take advantage of the fact that you can give it memory, so it can remember things within its own context from call to call, or you can create some state variables within the subroutines you define, and suddenly you've got subroutines that can remember things, and they can evolve, and they can do things even more implicitly. So we're dealing with multiple levels of being implicit, and that's really where the power of this is we're trying to get to as much. We're trying to give ourselves as much power to implicitly describe the thing we want to do as possible, and that starts with describing things maybe concurrently using the PRE, and then also utilizing global memory, and then giving our the scope value that gets passed from call to call, and then finally giving the subroutines memory, which I clearly think is pretty cool. Okay, this is anatomy of a very basic program that's using Subgenius, and it's really all it is. It's really three things. At the top, you describe the plan. I call it pre-plan, and that's a parallel regular expression. That describes the ordering or the constraints on how the subroutine should be called. Now, necessarily, if it's not obvious by now, any word that's in this parallel regular expression really needs to be implemented as a subroutine or handled in some way by autoload. But in any case, any word that is in this parallel regular expression is a subroutine that is going to get called. So the second part, or I should say, well, there's a PRE, and then there's the call to Subgenius to basically linearize or sequentialize the plan into some valid ordering, as we've been talking about this whole time. And then there's the call to run any. Now, it's probably better for me to just direct you to the man page or to the pod on Subgenius to look at the different ways to run things. But the most concise way that you can run a plan is by using run any. So when you initialize the Subgenius reference and you pass it to pre-plan, it's not yet serialized. You've just created this object or this instance of Subgenius. And then you can use run any. Run any pretty much encapsulates the things you need to do, like the call to serialize the PRE into a DFA, and then and also pick an execution plan or generate a string basically that describes the execution plan, and then iterate over this string, just calling each subroutine one at a time in order, and meanwhile passing in the scope variable. So what this run any call is doing, it's encompassing all of that. So that is the most concise way, and it's also saying that you're comfortable running in any of the valid sequentially consistent plans that are produced by this PRE. And what I would suggest is you not have a PRE that has valid orderings that you're not wanting to use. In other words, the PRE should give you a finite set the finite set of strings that you want to be able to execute over, or the orderings that over which you want to be executing. Your tolerance for the number of different valid orderings described in the PRE has a lot to do with the parallelism that is present in what it is that you want to do. If something is fully independent, embarrassingly parallel, as they say, then you don't really care the order in which these subroutines are executed. You just want them all run. It doesn't matter the order. Okay. Now you can use you can construct a parallel regular expression that does imply subroutines that need to happen in a certain order, where they need to happen in order. Parts of your execution where maybe there is some parallelism and some independence. So that's when you start thinking about how you really want the execution to go, and the parts that have to be executed in order and the others that don't have to be executed in any particular order. That it gets expressed, and you can express it very, very precisely using the parallel regular expressions. So that's the power. You should only be crafting these parallel regular expressions to describe the full set, or in other words, you shouldn't. The PRE that you're describing should not be producing orderings that you're not admitting is correct. That tells me that you need to reformulate your PRE. Hope I didn't get too deep into that, but that's an important point I needed to make. So I guess the third and final part of the anatomy of this script is that the subroutines are returned. And if you look at, so there's a begin subroutine, there's a step 1 subroutine, there's a step 2 subroutine, and there's a fin subroutine. On the left-hand side is the minimal DFA, and then under that I list there's only 2 valid orderings in which this PRE is describing that the execution can go. So begin is always first, fin is always last, and then the only, I guess, freedom you have or independence within the execution of where you're able to be implicit in your description is where step one and step 2 don't necessarily have to happen one after the other. They can happen in any order. And when you serialize it down to a single line of execution, that's what you're going to get. So you're admitting here that there's only 2 orderings in which this PRE is valid based on your description. I also wanted to point out, so let's just pick the begin subroutine. Like I said before, there is a scope. It's a hash reference that gets passed in to each subroutine call, so you can capture that in as, and that's pretty much how you handle parameters that you wish to pass in and out of the subroutines as the execution is going. As I said before, I call it the execution scope. Not sure if that's the right term, but that's what I call it. And then I also show you don't have to use a state variable that gives each subroutine a memory from call to call, but you can. And it's private memory within each subroutine. So in this case, I show it. We don't use it, but it's there if you want it. So some things can be done pretty cleverly by using the state memory. But this is just an anatomy of a program. And this is actually the template, not template, but this is the form that all the examples that I'm going to be showing shortly follow. All right, I've got a couple of tools that come with SubGenius. One is Stubby. This is kind of like the general utility. I found when I was creating these examples that there's some boilerplate involved, and I knew I was going to, given a PRE, I knew that I was going to need to define subroutines that were named the same thing as all the words in the PRE. So it makes a lot of sense just to automatically generate these subroutines. So Stubby can be used for that. Stubby can also be used for pre-caching these PREs. Because of the complexity of the algorithms involved, these PREs can take a long time to be compiled, and I'll use the word compile, down into a DFA. So I built into Subgenius the ability to cache PREs, and it happens automatically, much in the same way as inline C will not recompile programs if it detects that the shared libraries created for use have already been generated. So very much similar approach. I call it pre-caching in the tool. In conversation, I call it compiling because that's what it is. So Fash is it's an old shell script that basically provides access to a bunch of one-liners that are available through Flat. I plan on sprucing that up a bit, but it's what I can use to say dump the dot, the different finite automata and GraphViz format for visualization. But my goal is to move away from that and just use Stubby as the primary tool, not only for initializing code, but also allowing for pre-compilation to happen, and also for doing like debugging or introspection with any programs that people may end up writing with this. And I'll show some examples here shortly. Okay, so I've already touched on this, but it takes a long time for PREs to be compiled or converted into DFAs. This is largely algorithmically or computationally complex. The computational complexity is high, so there's only so efficient that the algorithm itself can be made, but other things can be done to make it faster. The conversion process itself faster. Writing it as an XS module comes to mind, but since that's not my forte, although I'm interested in doing that, my solution was just to provide some caching. And again, this caching is very similar to how inline C operates. And it actually, once you have a PRE that's been cached, it almost takes no time at all, because it just pulls the DFA right out of the storable format. Okay, now we get the demo. All right, this is what I let in with. It's a JAF demo, and that is an errant Z, so please ignore that. It's a PDF, so I can't delete it right away. But in any case, ignore that Z at the end. That doesn't mean anything. So this is the PRE for JAF. I thought this was an appropriate demo. Now, let's talk about the JAF PRE. All right, there's a beginning, there's an end, and then within the parentheses, there's JAPH, and they are all shuffled with one another. So this shows the parallel finite automata, the non-deterministic finite automata, and the minimum DFA that is produced from the JAF example. Now, you're saying to yourself, you're probably assuming that the J subroutine is going to print just, the A subroutine is going to print another, and so on. But since I wanted to simultaneously demonstrate I wanted to simultaneously use a classic Perl tradition and also demonstrate what we're doing here, that's not going to be the case. All right, so I think that what I'll do now is switch over to this view where I can run the demo. And I believe I have the code up. So let's go. I've got 3 different versions of JAF. And it's pretty straightforward. So I actually can delete that find bin stuff out of there because I'm using Subgenius as it's been installed on my system. This is just a big old comment. So this is the PRE, parallel regular expression right here. As I said, begin, end, and then JAPH. And then here's where I initialize. Let's give you some line numbers. So line number 29 is where I initialize the subgenius instance. And then here on line 31, I'm creating some global memory. So yes, I'm going to be utilizing global memory from the subroutine. So in most cases, I wouldn't recommend that, but in this case, we actually want to take advantage of the fact that this is provided for us by perl memory model. So this call here, init plan, that is the step that converts the PRE, so the JAF PRE in this case, into a minimal DFA. And that basically primes, it initializes our object for getting ready to execute. So then I have run once. Now, when you run on line 35, you run init plan, it's going to pick one of the orderings. You're not guaranteed which ordering you're going to be using. And again, what I said before, you should be describing your PRE in a way that you don't care which ordering you're using. Now, it might be beneficial to, and I have ways to iterate over the different ordering. It might be beneficial to do that in some way or for some reason. But basically, you don't have to worry about which ordering is first. So in other words, you're not going to serialize the PRE and then inspect the orderings that it produces. You rely on the fact that you describe your tolerance for implied unorderedness in the PRE, and you have some confidence that you're going to get a sequentially consistent serial ordering from that, and then so that should just be good enough for you. Although I do encourage you to look into it to gain that confidence. But that's the approach that this is implying: is you generate the PRE and then you run it. If you want to look and see which ordering it was running, that's cool. But it shouldn't matter. Your basis of control is how you describe the PRE. All right. So this run once. This is actually okay. So this is the main command that you use to execute the ordering, and the verbose. That's just an argument. That's something you can pass in to run some diagnostic information. Typically, that's off, but I'll show you what it looks like. It could be further developed to be more helpful. Now, this scope here, this is just a demonstration of I'm initializing the scope that is getting passed in to the first call. So this is the data structure, and if this isn't defined, then an empty hash is going to be passed into the first subroutine. It's called. The PRE was described in such a way that begin is always called first. So this anonymous hash that we've defined here with the scope keyword, or the scope key, is going to be getting passed into the begin subroutine first, and then passed on to subsequent calls. And that's pretty much it. So now, you may be wondering how this actually works. I'm going to run it. And you will see that it prints. And it prints consistently. Now, let's turn that verbose flag on just by passing something in. So what this is showing us, it's outlining the actual serialized plan that is being executed with this first line. And then under the execution colon, it shows you the output, which in our case is printing just another Perl hacker. And then underneath that, it's showing, and I have this in as part of this. That's not part of the diagnostic, the provided diagnostic part. What I'm doing here is I'm literally just dumping the contributions for each subroutine that's called. So going back to this, in our case, so begin is getting run first, then J, P, H, A, and then N. So just another Perl hacker. The J subroutine printed just. Makes sense, right? Okay, now the A subroutine printed, you would expect it to print another, but it prints hacker. And and then H prints perl, P prints another. Well, if you look at the execution order, we want to maintain. This is kind of a tricky demo, or a tricky first example. But what we want, because we're dealing with this specific ordering, we want our execution order to be oblivious to the ordering in which the subroutines were called. So, in other words, we want the first J. This could have been a P or H or A. We want the first subroutine that's being shuffled to always print just. We want the second one to always print another. We want the third to print perl, and we want the fourth to print hacker, comma. And then there's the end. So the way that this is done is basically any of the subroutines defined below, whether it's J, A, P, or H, will print what's next in the order of the string that we're expecting to print. So when, say, J is called first, it's going to record within, let's see here, it's going to record within its global hash that it's printing, let's see here, I'm even confusing myself. Oh, let's go back up to the machine. Okay. So within the scope, we're defining the ordering of JAF. So here we've got a list. We're creating an anonymous array, and it's composed of the elements just, and then another, and then perl, and then hacker. And then when a subroutine gets called, it's going to be picking. Let's see. Okay. So it tracks the order in which it's called using the scope variable cur or current. What's the current position that order in which the subroutine is being called? So in that case, it has more to do with the call ordering, or everything to do with the call ordering. So when J is called first, we're recording the actual word contributed by J as the element with the index of whatever scope cur is. And then that gets incremented and then passed on. So when J is first called, it's going to record actual as just. And then scope, that we record this here within the scope variable that gets passed in and out, within this contrib key that's passed among the different subroutines. The fact that I'm using this state variable, it doesn't really give us any benefit in this case, except to just confuse the example, which clearly confused me a little bit. But in any case, it shows you that you can save within each subroutine, things that it has done or has seen in the past. So if we were to create something that maybe called J again, then we could recall the fact that in a previous call it contributed the word just to this ultimate string. So in any case, the ordering in which the subroutines are called matters, and it simply just picks out the element that is in this JAF key within the scope. And then the string itself is built up in this contrib here as each subroutine is called. And then cur is initialized here. So this cur is just what index of the JAF anonymous array above it is the subroutine going to contribute. So then once it gets to the end, we know that fin is going to be called last. So we have fin actually doing the printing of this. Okay, that's a little more clear. So we know that begin is going to get called first, fin is going to get called last, And then in the meantime, J, A, P, and H are going to get called in any order. Well, by the time that end is called, we know it really is the end. And I guess I was calling it end or fin interchangeably, but in this example, it's end, begin, end. But since we know it's going to be getting called at the very end every single time, and we know that this contrib key within the scope context is going to possess the properly ordered words that come together to say just another Perl hacker. We're gonna join that in print, and that's where you get the printing. So so that's that. I've got a couple of other JAF examples. Let's see what the difference is here. This uses run any, so you can see that's the main difference here. Is it just uses it run any. I also don't use any global variable, but it is okay to access that if you want these subroutines to be accessing it. You can use the global variable, the global space, and I guess in the same way as maybe the scope context, but it can also be used in different ways. And I would actually encourage you to consider using them, discovering what are the best reasons and places to use those memories, because again we want to take full advantage of the memory that Perl's giving us. We have global memory. We have memory that can get passed in from, or an execution context. We're I guess adding this execution scope that can get passed in and out of each subroutine, and then you've got the state variables. So this is just showing run any. So there's no unlike in this first example here where we do the init plan and then run once. We're just creating the PRE, and then we're doing in one fell swoop the initialization or instantiation of the subgenius reference. We're passing in the pre-plan, and then we're just saying run any, and then of course we're passing in different keys that maybe the run once or run any would take, and then we're initializing the scope. Here works in the same way as the first JAF, and then let's see what the difference here is. So I guess that's what I mean by it's sequentially consistency oblivious. It doesn't. These subroutines are created in such a way where it doesn't matter what order they're running. This is to demonstrate full comments. So you can actually have comments within your pre-plan to make it easy to remember or to describe it. Those all get filtered out, and so it makes it pretty easy. Okay, so let's look at another useful example that I don't have listed on the slides. But I've talked about OpenMP before. This is not like using OpenMP with this, but I needed to show this example. All right, excuse me. So this is a parallelization of the computation of pi, and it's basically using the integration method of computing pi. So you have the function, a function that I'm not an expert in this, but pi can be shown as a function, and then you can basically compute the area under this function, and using some math, you can come up with the value of pi. I'm probably describing it very incorrectly, but in any case, the point is that this can be done in parallel because you're basically you've got this function, and basically you're just slicing up the function into rectangles and then computing the area of the rectangle, and then adding them up in a certain way. And that's generally how I guess integration but that's what we're doing here. So this is an OpenMP program, which of course is threaded, that is computing pi. And so I wanted to create a useful example that computed pi using Subgenius. Again, when it gets executed, it's all run sequentially. But I wanted to show that this could be described using the PRE, and then come up with something that kind of looks like pi. So here we have, and this is effectively you start and then you fork off into multiple independent threads. Each thread contributes its own piece, and then there's a reduction at the end where the values or the computations that each thread has done independently will come back together to give you a single result, and that result for us is pi. So this is the pre-plan. Number of threads here. This is used later on. But each one of these, step 0, step 1, step 2, step 3, step 4, step 5, actually there should be, there's 6 threads, they're all participating in this computation of pi. Now I'm using the run any, and let's see if I can shrink. That's not going to be helpful. All right, well, I'll show you what scope is. Okay, in any case, the scope that we're initializing here, and we're not using global memory, we're using the execution context. But we've got some that we're initializing at 0. Number of steps is going to be 1 million, so per thread it's going to iterate 1 million times. And then pi is undefined at this point because we don't know what it is. This is just printing out. So when this is called in this way using the run anyway, the final result or the final scope is returned. So I'm capturing it. So this single line here is executing everything and capturing at the end the final result. And then this is just printing out the final value of pi that we so anything below this subroutine, this comment block here, subroutine, that's your program. As long as you have the initialization or the execution of your program, as long as you have the subroutines defined, as you've considered them, then it will do the right thing. So in this example, I've got each subroutine defined explicitly. They all call this do calc. And then I finally have this reduce subroutine. So the do calc, it basically each thread is computing its own its piece of of pi, the value of pi that it's computing. And really, the only reason why there is a subroutine here for step 1, step 2, step 3 is to define that this is step ID 1 or step ID 0. Okay, so otherwise it's all boilerplate. But I'm going to run this to show you that it produces anything. And I will warn you ahead of time, this is not exactly pi, and it's not the whole point of it. So it's doing its thing, it's computing pi, it's iterating over millions of times, and then it gives us something that kind of looks like pi. I guess that's acceptable for now. So, but what's happened here is each of those subroutines have been executed in some order. Okay. So this is an example. I wanted to reduce the number of explicit subroutines because we're trying to write less code. And here I've got the same PRE, step 0 through 5, and then reduce. But here, what I've got, instead of defining each subroutine explicitly, I'm using auto load because I don't have the steps defined. I'm using auto load to get out the necessary information. So I'm getting the name. Really, I'm not even caring about the name. I want to make sure that the subroutine that's in the PRE is at least starts with the word step and it has a number on it. But what I really want to get out of it is the number that's at the end, because that's used as the step ID now. And then so this whole part of the auto load you may recognize is just looking at, okay, what it was called. And then the bottom part is dealing with calling it. Now, I'm getting, since we're dealing with scope that's getting passed into each subroutine call, I'm capturing it here under old scope. And then when I run it, I'm capturing the new scope. Now I'm running it using snap, which is just, it's like, prototypical or archetypal step, and it uses the step ID, and then the old scope. And then here, really it's just a wrapper around view count, which necessarily needs a step ID, and then the scope, okay? Because it updates, does it update the scope? No, it gets information from the scope, like the sum. Let me see here. Like the sum and, oh, okay. So I'm not assigning to scope within this do count, but I am assigning to scope within snap. Snap returns scope, and then auto load returns the new scope, and that gets fed into the next subroutine that gets called. I will show you that it runs. It may even give us the same answer as the first. There we go. Same answer. Now, it ran a little bit faster, but that's because we were caching. I will show you the cache directory. Those are storable objects that were generated from the PREs. And I can talk a little bit about how those are generated in a consistent way or detected. All right, final example is making it more implicit. I have the same step listed 6 times, okay? And I'm calling it the same way. But this time, I've got no auto load. I've got a single subroutine called step. I've got the reduce, which is the same in all cases, and I've got the do calc, which is the same in all cases. So what's happening here? We're using the state keyword to track and increment the step ID. So each time this is called, step is called, step ID is 0, step ID is equal to 1, and then go all the way down here. And keep in mind that this is going to still result in the valid PRE because it supports comments in this way. Step ID is equal to 5. So we're taking advantage of the fact that the step function, the step subroutine, can remember through the state variable step ID what it should be using for step ID. And here's where it's incremented. And sorry about that. Line 36 is where it's incremented. And there we go. All 3 of those programs are equivalent. Some are more implicit than others. But it's giving you, hopefully it's giving you an example of what can be done. Now, I can show you Stubby very quickly. So one thing I added a couple of features for Stubby during this talk because I wanted to be able to generate and list all the valid orderings in that way. So we can let's see. So like step 0, step 1. We're looking at this is the PRE that was in the Pi example just now. Step 2, step 3, step 4, step 5, close, reduce. Now, list subcommand. Oh, sorry. -P. And since we already ran it, it's pretty cute. Now I'll show you something here. I'm gonna blow away all of the blow away the cache directory, and we're gonna time this just to show the cache effect here. So here, say it took about 5 seconds of real time. Okay, time to solution. If I were to run that again, most of that time was actually spent converting the parallel regular expression all the way to a minimized DFA. So here, it runs almost immediately because of the caching. So huge savings there. Let's see. Now, if I wanted to just pre-cache and not do anything really with it, that's where the pre-cache command comes in. Study pre-cache. And then when it finishes, it's going to give you the path to the storable object. Now what we can do is I can show you that let's time this. So since that was the same PRE, it ran almost immediately. Now I'm gonna blow away the cache directory again and run that. Probably take about 5 seconds or more, slightly more than 5. Oh, okay. Let's try it again. I deleted the cache file again. So, all right. So system dependent, but say between 3.5 to 5 seconds. If I were to run this again, I'm not deleting the cache file and run computing pi. Boom! It happens super fast. So you know. Now, what is a PRE that like goes off the rails computation or complexity wise when you want to like make it super slow? Well, the more shuffles you have, and let's see. We'll see how long this takes. Oh, that's not taking any time at all. So, A, B, C, D, E, F, G. See how long that takes. Alright, so that's 4 seconds. A, B, C, D, F, G, H. We'll throw an I in there. Taking a little longer. I may have to end up killing it. So this will actually lead me. So check out Stubby. Stubby can also help initialize programs. Well, I'll give an example of that here, just so you know. It's working too. I'm gonna kill it. Well, maybe H would be faster. Well, in any case, this points out a good, a cool thing that I was playing with. Let's see, in examples. Let's see, I've got the pre plans now. One way to get around this, in addition to caching, I think that there should be like an actual solution and not just the caching one. These take all these stubby commands will take files too, in addition to PRE. Now, what I have here is this do lazy here. So say we have this monster PRE. You can actually save time by lazily sequentializing PREs. Okay, so this do lazy SEQ actually contains within it. I need to find the example, but it contains within it that subroutine call. So each of these are subroutine calls. Init, sub A, sub B, do lazy sec, sub C, sub D, fin. Do lazy sec is within it contains a new instantiation of subgenius and another PRE. So if you have this monster PRE that you've created and you want to save some time and lazily sequentialize it, you can do it in this way. Why did that not come up? Okay, in any case. Well, here's the example of the do lazy, which is probably interesting to me. So this do lazy down here, you can see it's got itself an inner plan. Now I'm not going to sit here and try and show you how long it takes to compile the non-lazy form of this, but I can run this script here. I just show you that boom, it works. So what happens is the order operations basically is it sequentializes the top level PRE, and then when it hits the do lazy subroutine, within that subroutine it hits another PRE, and then it then will compile that, and then it will execute that. Now you just need to make sure you define the subroutine in place. Now finally, I'm going to show. Stubby init. Oh, let's do stubby init f pre-plan lazy. So I'm going to initialize the Perl script using that pre-plan. Okay. So we'll just name it x.pl. It dumps out the standard out. So anything else? Okay. So this literally, that call just created all of this. So if you know the PRE that you want to run, then okay, yeah. So if you know the PRE that you want to run, so when I created this examples, when I created this program, I literally just did what I showed you there, except for the do lazy here. What I did was just added a PRE, added another call to subgenius. You see, what I did here is I'm not even creating an instance. I am passing in the scope that was passed in do lazy, and then I'm just run any, boom. So what that is, it's gonna allow you to express PREs even in subroutines that you're calling through the original PRE. So you could have a hierarchy of nested PREs that don't take forever to compile and can do some pretty interesting things. All right, let's. Subgenius has a very long and interesting, or excruciatingly, painfully long, however you take it, Perl doc, and I'm trying to make sure it's complete and legible, or readable. That makes sense. So lots of stuff to explore there. All right, I'm gonna go jump back to the PDF and finish this thing. All right, way forward. So this gives us, to me, I think this gives us some at least some way to express parallel semantics. And then it allows us to do so in a way that exploits Perl's uniprocess model. So we can get the implicit a way to implicitly define programs within this uniprocess context. Now, the examples I showed before were kind of, I say fork join in OpenMP. In OpenMP, that's kind of like a high-level threaded interface to programming for C, C++, and Fortran. There are sections within the code you can generate, or you define these parallel sections. That's referred to as a fork. In OpenMP, within their own literature and papers and whatnot, they refer to it as primarily a fork join paradigm, meaning you have a sequential program, you break out into threads, each thread does its own thing, you've got shared memory, and then there's the point where the parallel section ends, and that's the join, and then it can proceed. OpenMP also has tasks and things like that, but that's not really what I'm talking about. So this gives us, right out of the box and very clearly, fork join semantics. I'm not talking about system forking. I'm not talking about array join. I'm talking about the creation of parallel sections, or at least for us, as far as it helps us in being able to describe them semantically. Other things that I'm going to be looking at, I'm sure that there's a way to do async, and await. That's not supposed to be away. It's supposed to be await. But I'm still trying to wrap my head around what futures are in this uniprocess context, and this actually is one of the things that made me start thinking about this. Is I kind of get what futures are. I know what async is. I know what await is. I think so. I do anyway. I know what futures or promises and that kind of stuff are. But it doesn't make any sense to me about what that means in the uniprocess context. How would I even describe that concurrently? So I think that there's a way to do it, but when I start thinking about it that way, it just kind of falls apart on my hand when I try to think about it. So I just need to think about it some more and talk to some other people that I know what they're talking about. That's what I intend to do. And maybe there's some other paradigms that might be interesting for us to look into. Okay, so during all of this, I started thinking, well, especially when I implemented the scope, the execution scope that gets passed in and out, I was thinking this is very pipeliney. So let me search for something like this, at least something related to subroutine scheduling on CPAN. And the first three were probably the biggest hits. There's Pipeworks, Subpipeline, and Process Pipeline. Those are interesting. Take a look at them. I think that this approach it's just different from those. So take that for what that means. There's the flat module, which is what is utilized to convert the PRE to the PFA, and PFA all the way down to the minimized DFA, and that's how we get our strings, or our AKA our valid execution paths, from the parallel semantics provided for in the parallel regular expression. So that's really all Subgenius does, is it gives us a convenient interface interface to go from a PRE, where the words are subroutine names, down to a linearized schedule equivalent or valid, sequentially consistent schedule of what those subroutine calls would look like. And then graph PetriNet, I haven't really had a lot of time to play with this. I said before, a parallel finite automata is equivalent to a binary PetriNet. I would like to see if there's an opportunity for me to integrate or to use graph PetriNet somehow in flat, but we shall see. Flat provided all the capabilities that I needed to provide the wrapper that Subgenius is, but I'm still interested in the topic, and who knows, maybe I'll discover, I'll find out about a new regular operator out there that might help in some other interesting way. And I am on the hunt. I tried to find a list of all regular operators over regular languages, and for some reason I can't find them. I have a couple of people I can ask that would probably know, but if you know, let me know. Good reads. So this point one, it talks about the shuffle of languages. It's on Planet Math. It was pretty good. Leslie Lampport's paper where he introduced sequential consistency. Now we talk about number 3 is it's an interesting. It's not the PDF I was looking for, but it's still good on memory models and what they mean typically in the context of multiple threads or SMP. Number 4 is a video from Teo Desian, who he and I have talked quite a bit about sequential consistency and the async stuff. So I would definitely recommend checking out some of his videos. And then there's number 5, Introduction to Automata Theory and Languages, which I pointed out. And I had a copy somewhere. Here it is. I meant to show it. Before, but I also have a book on OpenMP, which is interesting. Okay, enough of that. Oh, I didn't list the paper by Stotts and Pugh, but look up Stotts and Pugh, Parallel Regular Expressions. It's from 1994. Conclusion, PREs can be used to describe semantically parallelism, and we can use it as long as we can get it down to a sequentially consistent form. When describing execution order of subroutines, we can use it to describe things concurrently and execute them consistently in a UD process. But no, there's lots of work to be explored here. Hopefully there's some interest in it. I'm happy to answer questions, and I'd be thrilled if people found bugs in their feature requests and whatever. So, open questions. I kind of went over this before at the end in a rush, but there's some opportunity here at some point. If people start using this, there's some opportunity to either figure out how to get some actual parallelism out of this. Like if we get used to expressing things concurrently, it might be a step in the right direction to get us talking about and thinking about actual shared memory parallelism within Perl, and seeing if there are parts of Perl that can be parallelized. I know not all of it can be parallelized. I know that the data structures are necessarily an unforgivingly UD process and require the safety that gives. But there's probably lots of other places in Perl that could be made parallel or introduce some shared memory parallelism. I think if people who are interested in this look closely enough, we will find that there's a tremendous amount of things within Perl now that can be used for this that maybe wasn't thought of to use it in that way, or maybe not enough people showed interest. But I'm confident that we have now, or we are very close now to being able to provide some really nice intuitive interfaces to real shared memory parallelism. But in the meantime, it's still enjoyable for me to start thinking about these problems and get feedback from people regarding the approach that I'm suggesting here. And that's it. I will stop the recording. Hopefully everything recorded properly. And this isn't too terribly long. But again, I'm happy to answer questions. You can find me online. Not hard to find. And just let me know if you have questions. And good luck. Have a good day, good evening, and good night. And